So before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. So here this is the very important topic from nuclear physics, that is semi-empirical mass formula. So according to the liquid drop model, which can be used to obtain an expression for binding energy of the nucleus. Liquid drop model is one of the model that is used to explain about the properties of nucleus. So according to this model, we can just derive the equation for binding energy. So in 1935, Van Weizsäcker expressed the atomic mass of nuclide in terms of series of binding energy corrections terms with the main mass contribution from proton and neutron. So the modified expression of the mass is known as semi-empirical mass formula. So formula further modified by Bethe and others, but the main outline remain the same. So the mass can be expressed as that is the number of protons, number of neutrons minus the binding energy. So here you can see Z is number of protons, number of neutrons, MP mass of each proton, Mn mass of neutron, and this P corresponds to the binding energy expressed in terms of mass unit. So here for this B, we have to calculate the correction terms. So the value of B is calculated empirically as made up of number of correction terms which are mentioned here, related to volume, surface, and Coulomb energy, and asymmetric energy, pairing energy. So these correction terms, adding these, we will get the value of binding energy. So here we have to note down, according to our earlier study, the binding energy is the energy obtained by converting the mass defect of the atom. That definition you should understand: the difference between the sum of the masses of the individual nucleons in the nucleus and the actual mass of the nucleus. That is what we call mass defect. So when the mass defect is converted into energy, it gives binding energy. So for that we are finding out the correction terms here. So this binding energy obtained by conversion of mass defect is not accurate value. So that's why it requires correction terms, which is given by semi-empirical mass formula. So the first correction term is volume energy correction. So it has been found experimentally that the binding energy per nucleon is approximately constant over wide range of mass number. Volume, if we consider, we have to take the mass number here. So it has been assumed that total binding energy of a nucleus is approximately proportional to total number of nucleons. So then we can write here volume energy is proportional to mass number. So AV is what? Empirical constant. Semi-empirical means it is involving the explanation of theoretical and experimental aspects. Second one, surface energy. Here a molecule at the surface of a liquid is less attracted as compared to the molecule in the interior. If we take liquid as an example, that is going to be considered as nucleus, then the molecule outside and the inside, how they are going to be attracted, that is the idea here. So nucleons at the surface of a nucleus are bonded to be less tightly, and the nucleons that are interior have the which are tightly bound. So the number of nucleons on the surface are proportional to the area of the nucleus. So nucleus having radius capital R has an area of 4 pi r square, that we know. So the surface area reduces the binding energy. That's why it is proportional to a to the power 2 by 3. Here it reduces the binding energy, that's why minus term, which is a empirical constant. So the third one, Coulomb energy. Coulomb repulsive forces are produced due to the mutual repulsion between protons which are positively charged. This also reduces the binding energy of the nucleus. So because two positively charged particles repel, so this is the negative contribution to the total energy. So here the Coulomb energy of a nucleus is work done in bringing z number of protons from infinitely into the volume equal to the nucleus. So then we can write this Coulomb energy as z into z minus 1 divided by a to the power 1 by 3. So here again this is what the negative sign indicates, empirical constant. Negative because it is due to the force that opposes nuclear stability. So the fourth one, asymmetric energy, as the name indicates, here there are unequal number of protons and neutrons, and which are more stable, that is n equal to z is called symmetric effect. If they are not equal, that is asymmetric. If equal number of protons and neutrons are there, that is nucleus is going to be stable. If it is not, then we can say nucleus is unstable or asymmetric energy correction. So again this is also going to decrease the binding energy. That's why we are going to have here again negative term into a minus 2z square divided by a, where ar is another empirical constant. So for fifth one, pairing energy. We know that the nuclei containing even number of protons and even number of neutrons are more stable than the odd number of proton and odd number of neutrons, which are less stable. On the other hand, the nuclei containing given number of protons and odd number of neutrons or vice versa are intermediate stable. The correction term delta is positive for even and negative for odd number of protons and neutrons. So delta equal to 0 for odd number of protons and even number of neutrons. Then here we have the pairing energy, that is given by this last term, a into delta divided by a to the power 3 by 4. If we add all these 5 correction terms, we are going to get this binding energy equation. So first term is volume energy correction, surface energy correction, Coulomb energy correction, asymmetric energy correction, and pairing energy correction. So this is all about the semi-empirical mass formula, including binding energy correction terms. So